Let us also now realize one thing. When we are talking about forces and moments, we are talking about forces and moments along x, y, z direction, moments about x, y, and z direction. Whatever we have learned so far, that was, I know the CL, I have written function of alpha and delta E. Then as far as moment is concerned, Cm I have written again function of alpha and delta E. Let's say when I come to Cy, side force coefficient, again it is function of beta and delta R, and Cn was also function of beta and delta R, and Cl rolling moment coefficient was function of delta A and beta, or let me write beta and delta A. Let me explain this. The first, when I talk about Cl, we wrote Cl equal to Cl alpha into alpha plus Cl delta E into delta E. Similarly, for Cm, we wrote Cm alpha into alpha plus Cm delta E into delta E. We are now going step by step. We are taking the first case. So I can erase this part. But what was the understanding? Here, of course, there should be a Cm naught, and there should be a Cl naught. What is the understanding here? Understanding is, this is the lift coefficient, this is the moment coefficient, in a condition where the aircraft is having an alpha and an elevator is deflected by delta E. There are no dynamics like this. It is a steady state type. Okay? But when I am writing equation of motion, the whole airplane, I am giving a delta E. Actually, airplane will have some transient, then it will go to the steady state. So, what happens if an aircraft is perturbed by or disturbed by giving an elevator? It starts oscillating in this direction. There is pitch up, pitch down, pitch up, pitch down, or it's oscillation about y-axis. Right, and that is, if you see, this is my x-axis, this is my y-axis, and this is z-axis. So there will be oscillation about y-axis, and we say that is q, that is the pitch rate. What is the meaning of pitch rate? At what rate this attitude of the airplane is changing, oscillating about y-axis, this pitch rate. So now you will see, because of this dynamics, Cl will not only be function of alpha, also be function of q and delta E. Q will show you how this pitch rate also will change Cl. Right? Similarly, you will find, if you go further analysis, you will find it not only depends upon alpha q and delta E, it also depends upon alpha dot, that is at what rate angle of attack is changing. Okay? We will explain why this happens, but I am just building up so that we can develop expressions. So, if Cl is like this, then Cm also will be a function of alpha dot q delta E. Now see, from static case, it was just function of alpha and delta E. Similar, Cm was function of alpha and delta E. But the moment we are talking about dynamic case, when allowing the oscillations, something like this, so there is a q, pitch rate. So that we are saying the Cl also will be function of q, not only q. As the airplane does like this, the velocity vector and the axis, their angle changes, the angle between the velocity vector and the axis changes. So there is a induction of alpha dot. So if the Cl also will be function of alpha dot, and since Cl will be function of alpha dot, q and delta E, Cm will naturally be also function of alpha dot, q and delta E, because Cm is nothing but Cl multiplied by a length. Okay? So now the challenge is here. You will find for a highly dynamic aircraft, highly maneuverable, high performance aircraft, this Cl will be function of even delta E naught. With what rate you are moving the elevator? That also becomes interesting variable to model the Cl. But we are not going for such a high performance aircraft. We are going for a conventional aircraft where the CL is modeled like this, CM is modeled like this. So now let us take CL. So what we are seeing, we will go very slow in this. CL is function of alpha. I write Q, then I write alpha dot, and then I write delta E. Okay, so I can write CL equal to CL naught plus CL alpha into alpha plus CLQ. Let me write QC by 2V. I'll explain you why we write like this, plus CL alpha dot into alpha dot C by 2V plus CL delta E into delta E. Normally, if I give you expression like this, you will write CL equal to CL naught plus CL alpha into alpha plus CL Q into Q plus CL alpha dot into alpha dot plus CL delta E into delta E. But you have seen here, for Q, I have replaced by QC by 2V. For alpha dot, I replace by alpha dot C by 2V. Okay? Why? Let's understand. You see, these are all dimensionless, alpha, delta E. Okay? But if you see that Q has a, what is the unit of Q? Radians per second. So this is not dimensionless. What is alpha dot? Again, radians per second. So time is there. So these are not dimensionless. But all other are dimensionless, motion control variable or motion variable. So we want to write CL using all non-dimensional motion variable. Okay? So what is done? If Q is radians per second, the unit wise, right? Then what we have done, we multiplied by chord, mini-atomic chord, and divide by 2V. Many literature, they divide by V. And what is the dimension of this? You see, radian per second, then meter, then of course meter, and here is second. So this all cancel. So again, this become dimensionless. Radian is dimensionless quantity or unit, right? So now what has happened by changing Q to QC by 2V, we have made this dimensionless, and we have modified CLQ. If I use the first definition here, then CLQ will be dCl by dQ. But in this way, when you are defined, please note that CLQ is dCl by dQ C by 2V. Correct? Not this. So this is non-dimensional quantity. Okay? This is CLQ means dCl by dQC by 2V. Physical meaning is what? What is the change in CL because of Q? If there is a Q positive pitch up or pitch down, how much CL is going to be changed? That is this derivative will tell us. That gradient it will tell us. Similarly, what is d? CL alpha dot? CL alpha dot will be dCl by d alpha dot C bar by 2V. Please note down this. Again, this has been made non-dimensional. So this is not the way we are defining. Not the way we are defining. We are defining CLQ as dCl by dQC by 2V, CL alpha dot as dCl by d alpha dot C by 2V. Okay? This should be clear. Now we need to know each of these derivatives. What is CL alpha? What is CLQ? What is CL alpha dot? And what is CL delta E? If I know this, then when I am writing the equation of motion, if I know what is the value of alpha, what is the value of Q, what is the value of alpha dot, what is the value of delta E, I will know how much CL it is generating. As simple as that. That is the beauty of this modeling. I repeat again, if I know the values of CL naught, CL alpha, CLQ, CL alpha dot, and CL delta E, then when I am writing the equation of motion, then to get the CL, I need to know the value of alpha, Q, alpha dot, and delta E. Since I know other things, I know what is the CL the airplane is experiencing. Correct? Okay. That is the purpose of writing this in this fashion, and also to put an effort to know, can I calculate CLQ, can I calculate CL alpha dot, can I calculate CL delta E and all the derivative based on the geometry of the airplane and the flight conditions, right? So let us focus on Q derivative. When I write Q derivative means, you know, back of your mind, it is basically we are talking about QC by 2V, right? Because this is non-dimensional. So let us see, will there be any CL because of Q or not? Okay. So how do I visualize? Let me take the horizontal tail part of the airplane. Let me consider horizontal tail of an aircraft. And let's say this is the airplane is going for positive Q. Positive Q, why? Because pitch rate. Q is the pitch rate, nose up is positive. As you know, this is our X and this is Y. So rotating about Y, nose up is a positive pitching moment. Now the moment it rotates about Q, what happens? This tail goes, let's say AC of this tail, somewhere here, let's say, I concentrate. This will be going down with a speed Q, and this length, you know by now, is LT. So if this is going with Q, what is the speed at which this point will go down? This V equal to omega R, so it will be Q into LT. Is it clear or not? For example, if I take this example, this is tail and it is going, so it's a pitch up positive Q. If it's pitching up positive Q, this tail is going down. So relative area, this tail will go down with what speed? With Q into LT, omega R, V equal to omega R. And as it goes down, I can always say the relative area will be coming in the same magnitude in the opposite direction. So what will happen here? Since this is rotating like this, the AC at this point will go down with the speed QLT. So I can say relative air will come with a speed Q into LT. No doubt? I repeat again, as this airplane is rotating with Q about CG, this tail is going down with a speed QLT, especially the AC of the tail. And since the tail is going down like this, I can say relative air is coming with a speed Q into LT. Remember, this airplane is moving also with a speed V. So delta alpha introduced at tail will be how much? Will be Q LT by V approximately. The vertical component and horizontal component. If this is the increase in angle of attack, what does it mean? It means it will generate lift here because of delta alpha. So what will be the lift? Delta L will be half rho V square at tail into S tail into CL alpha tail into Q LT by V. No objection? This will give what type of moment about CG? Because of Q, the lift is here, upward. So what type of moment it will give? It will give a nose down moment, right? Or delta L, to be more precise. So you could see that there is an increase in lift because of Q, and this lift delta L will give a moment which is negative. So delta M I can write as half rho V square tail, S tail, CL alpha tail, Q LT by V into LT. Do you think this is the right expression? What I have to take care? Remember, when I am writing moment and all, we need to be careful about the sign. What is happening? Because of positive Q, delta L is like this, that is giving a nose down moment. So delta L is giving a nose down means negative moment. So I have to ensure here, so I have to put this here, minus sign here. Now it is perfect. So we have got two expressions now. Let us see how can I generate Q derivatives. So delta L equal to half rho V square tail, S tail, CL alpha tail into Q LT by V. So what will be delta CL? Will be delta L by free stream dynamic pressure into S reference, that is delta CL, or I write delta C capital L, because small l is for rolling moment. So this will be now equal to this divided by this. You are expert. This is neta ST by S, right? CL alpha tail Q LT by V. What is our aim? We want to find out what is the expression for CLQ. What is the definition of CLQ? It is dCl by dQ C by 2V. So from here, if I divide this expression by, say, delta CL, let me write this, CL equal to neta ST by S CL alpha tail Q LT by V. So if I want to find CLQ, which is dCl by dQ C by 2V, because it's linear, so I can divide this by QC by 2V, and left hand side I will get CLQ as per the definition here. So what happens here? Once I put this, I see this goes off, V and V goes off. So I have expression for CLQ as 2 neta ST by S CL alpha tail LT by C, and by now you are expert, you know the way to write this, ST LT by SC into CL alpha tail, correct? 2 neta. Are you familiar with one of the popular expression? This is the popular expression, and that is 2 neta into VH into CL alpha tail. VH is the tail volume ratio. So what is the message? Message is, if I know the tail volume ratio, if I know CL alpha of the tail and neta will be around 1, I can easily calculate CLQ, because CLQ is equal to this expression. Why I want to find CLQ? Because I want to know what is the CL during the flight when there is a Q. So if I know CLQ, and if I measure the value of Q, I can find how much is the contribution here, right? Now, this is the first expression. Now, see this delta M. What is happening delta M? When I expand Cm, in similar way, you know, this will be Cm naught plus Cm alpha into alpha plus Cmq into Qc by 2V plus Cm alpha dot C by 2V plus Cm delta E into delta E. By now, you know how to calculate Cm alpha, you know what is Cm naught, you are also knowing what is Cm delta E, they are all static case. Now we are trying to go for dynamic case. So we are trying to find Q derivative, okay? That is, what is the change in the force and forces and moment because of Q, pitch rate. We have already found out the expression for CLQ. We will now find out the expression for CMQ. What will be CMQ? What is the expression? Can I estimate it, compute it approximately using some expression, right? So we will now come back here. We have seen from delta L to delta M is this expression. So if I want to have delta Cm, that will be delta M divided by half rho V square S C bar. Okay? So this will become, again, you are now expert, neta ST by S LT by C bar CL alpha tail Q LT by V. Okay? So what is the expression we got for delta Cm? Just write it here. And don't forget, our aim is to find CMQ. Right? Our aim is to find an expression for CMQ, which is nothing but dCm by dQ C by 2V, C bar by 2V. So we have got the expression of delta Cm is equal to minus neta ST LT by S C bar into CL alpha tail into Q LT by V. Please remember, whatever CLQ expression you have derived, and now CMQ you are deriving, these are primarily only for the horizontal tail contribution. So we have to similar way find out the contribution because of fuselage and wing. but we are trying to find first the expression for tail contribution, because we know that is the primary component which will add these derivatives, right? So this is, of course, I repeat, we are all now focusing on tail, which is the horizontal tail. So now our aim is to get CMQ. So CMQ is delta Cm by QC by C bar by 2V. This is equal to minus neta ST LT by SC bar CL alpha tail QLT by V divided by Q C bar by 2V. So what is the final expression? You could see VV gets cancelled, Q goes here. So you have CMQ as minus 2 neta VH CL alpha tail into LT by C. Such a neat expression. What is CMQ? CMQ is minus 2 neta VH CL alpha tail LT by C. You could see one thing very interestingly, that if we change LT, if we change VH, that means if you are changing VH, CMQ is largely affected. And also if you change LT, this also will change CMQ. Suppose you want to increase CMQ. CMQ means what? Damping. No? So this will tell you that if I want to increase damping, increase LT or increase VH or both. Okay? This is extremely important what you call derivative. I am now focusing only on the derivative. I will come to the physical significance of it as we are clear what does the derivatives mathematically or empirically looks like, right? With a little bit of insight, you could see that why I am saying the CMQ is a damping derivative. I like to explain you immediately now, because now at least you know what is the expression of CMQ. Before I explain what is the nature of CMQ, let me explain first CM alpha, right? And I will take you back to all those examples of mass spring. If you remember, I have been giving this example. So we wrote mx double dot plus cx dot plus kx equal to f of t, where this was stiffness and the C was damping constant, right? How to define a damping constant? C? The restoring force or moment is proportional to the rate of change of displacement. So this constant is the damping constant. And the constant which tells you the amount of force or moment which is proportional to the displacement only, that is stiffness. So this is rate of change of displacement and this is displacement. Here you see when you are talking angular stability, alpha is like x here and q is like x dot here. It's the rate. Okay. So this moment whatever delta Cm is coming because of q, it is proportional to the q. You could see that what is happening here. How this moment was generated? There is a delta L. Delta L has a q here. If q is there, delta L is there. Delta M is also again, this delta M is coming because of q. Right? So if q is positive, delta M is negative. So this restoring moment is proportional to q, to the rate. That is how CMQ we call it damping derivative. Cm alpha, the restoring moment is Cm alpha into alpha, right? So it is proportional to alpha. So this is stiffness derivative. Stiffness derivative. Right? This is stiffness, you understand how stiff is the spring. From that analogous to K, as a stiffness, this is called spring constant, and this is analogous to the C, which is because of the medium or the fluid. Now you understand, if you want to make an airplane dynamically stable, you not only need something like K, also need something like C. That is, you need to have stiffness as well as damping. And that is why we are now developing this expression, and we will ensure, I see that our airplane has both static and dynamic stability. In general, for normal case, if an aircraft is dynamically stable, it is statically stable also, right? But we will be doing our job in a manner which will not only make us understand what is static stability, what is dynamic stability, and how they are coupled, okay, in terms of response.